Yes, because if I start from it, I will start.
Yes.
So A4. Uh, so for after people studied the Painlevé equations, uh, they found in maybe some in some applications some equations which are key difference in and which in limit go to differential Painlevé equation. So this is U Painlevé 6 equation. So mhm. I will explain now. Yes, yes. Okay, so so what does so and people decided that so there are of course a lot of forms. You can imagine a lot of Q difference equations which in limit go to differential to the six.
But Anton, just a naive question. No? You write the two equations for two variables. So are these the Q analog of the Hamiltonian form of Painlevé?
Yes, yes.
Okay.
Yes.
So in some sense, G has to be written as P and Q or
Yes, yes. I will present you the limit precisely.
Okay.
Okay, so so here what we have. So f and j is a functions of variables a. Yes. Here we have six variables a to a5, which correspond to the d5-1 Lincoln diagram roots. So a0, a1, a2, a3, a4, a5. F and J. And bar down is a dynamic of these variables such that bar up corresponds to A2 goes to A2 times Q, A3 goes to A3 Q minus 1, where Q is A0, A1, A2 square, A3 square, A4, A5. So in fact, we can think about this parameter that there are six parameters with such dependence. So we can, for example, decide that Q is fixed, and of course Q is preserved by this dynamics. And yes, yes. So it is these powers is the coefficients of imaginary root. So a is corresponds to the roots, root variables, and q corresponds to the imaginary root. Imaginary root delta. Okay, so yes, it is bar up bar, and under bar is up bar power minus 1. So in fact we see that so we see that A0, A1, A4, A5 is constant parameters, and we can choose A2 or A3 to minus 1 as variable z. Yes. So for example, we can take z equal to A3 minus 1, but it is just for yes. So A0, A1, A4, and A5 stay invariant. Yes, for this equation. Don't hurry. Now we don't have still we don't have any signs. We have just this Q difference equation which accidentally have such correspondence to root variables, and now I will explain why. So another question you can ask. You see that in fact the direction of the dynamics is different in first equation and in second equation. It's for it is for convenience. So in fact, when we have some f and g at some point, then using this equation we calculate f and g bar, and at the second point we calculate f bar g bar. Yes, using this equation we can take bar, yes, and here will be bar, and here A3 will be shifted on Q, A3 minus 1 will be shifted on Q, and we will obtain the second equation. Yes. So to calculate, to shift, we should use this equation successfully, not immediately both. Okay. So for convenience, for removing bars, it is written in such form. Okay. So because so of course you can for example take bar and substitute from this equation to this equation, but the result will be horrifying. Okay. So just as for differential equations, with this equation we can ask for ask about space space of initial data. So what you see? So there are with difference to, okay, so let me start, then I will explain the peculiarities. So what is the let's focus on this equation. So you see that here you have 0 or divided by 0 for g equal to 0, f equal to a2 or a0, a2, and also g equal to infinity, f equal to 1 and a1 minus 1. Yes. When we see this equation, we have g equal to a3 minus 1, a3, a5 minus 1, and if f equal to infinity, we have g equal to 1 and a4. So in fact, we have from these two equations, we have already 8 points which should be blown up. Of course.
If I put g equal to infinity on the first it is a underscore will be equal to a1 minus 1, right?
Yes, if you yes, that's right, that's right. And I will speak about just about this now.
This should give me a relation between the constant value of x or 1 a1 minus 1. So to the constant value of x that f underscore a1 minus 1. I mean, if you consider the two equations together, and you see that
Yes.
this consistent. Is it f underscore?
So so for example, okay, so to do in fact, to do this more accurate and precise, you should not write infinity, but change the p1 times p1 map. But in fact, these equations are very symmetric under such change. You see. Well, so let's take some some points. For example, f equal to a2, g equal to 0. You see that. So so we should we should introduce new variables, which are f minus a2 over g and sorry. Okay, g, yes. So we should introduce this new coordinates. So f tilde g tilde. Then you see that f is equal to a2 plus f tilde g tilde. So you see that g tilde bar equal to a4 f tilde sorry, f tilde um, um, plus u2 minus a1 minus 1. So so you see that for general A's we have already no problems with 0 over 0. So you see that so f tilde cannot be infinity, because this is the case when this is like a vertical leaf. There is a difference between vertical leaves in differential and equidifference case, but I will explain it later. Why? So so and if f equal to 0, for example, then this f tilde, then there is no no zeros here. And if, for example, this one equal to 0, this will also not equal to 0. Yes, so so there is no additional blow-ups at this point. And of course for the first equation in this point there is also no problem, because there was no problem before the first blow-up.
Is it a kind of canonical maybe preserve some kind of synthetic structure or whatever?
No, because you see the symplectic form is multiplied or divided by g. But this is okay, because because the symplectic form, as I explained, after blow up, we should add to the canonical class the exception divisor, and this is visible here. So we can take any form with any coefficients, but we see that df over dg became df tilde dg tilde g tilde. In this map.
Symplectic form which corresponds to important factor
I think yes, but so you say that df dg over it goes to a2 plus f tilde g tilde so g tilde is removed.
An extended symplectic structure, maybe
Uh, so this is codifference equation. So this is not a Hamiltonian system in ordinary way, but but nevertheless we have some corresponding integrable system. Yes. So partial.
But do you want to consider it as a autonomous system on bigger phase space or not? But probably that's not make much difference.
So so you see that that after the blow up, yes. So 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 maybe I should repeat my argument. So the canonical class does not depend on the coefficient we use, but maybe Pasha, what can you repeat your question, please? Or ah, okay. Well, so so and of course of course the same things will happen for all other 7 points, because in fact they are all similar. Yes. So also you should check the following. So for differential equation we had some some differential infinitely small dynamics, linear, invertible. Here we should really check that for the Q difference or difference equations that we have exhausted all blow-ups more accurately. So so here we should check not only just these equations, but check that such 8 resolutions is enough for infinite dynamics in both directions. Yes. So what I am talking of when you have, so now what we had 4 lines, 4 coordinate lines, g equal to 0, infinity, f equal to infinity, f equal to 0. and here we have blow-ups A2, A0, A2.
No, but the second should be G equal to infinity, so one of the two should be G equal to infinity.
Yes. So here we have 1. Here we have A1 minus 1. Here we have A3 minus 1, A3 5 minus 1, 1, A4.
Yes, category, one of the two lines of the horizontal ones should be G equal to infinity.
Ah, you are asking about it? Yes. Okay. In fact, it is like I think I'm already thinking about a differential limit, because this limit is when we take this line and go into this. So I will explain. So you see that this is we obtain here minus two curves. Yes. So with dashed I will denote minus one curves. With bold I will denote minus two curves. So what is the question? That so we see that for so for the first dynamics we have for the first dynamics we have f and f and g bar. So one moment. What I want to say. One moment. So it could happen that so what can happen? We know these bold lines remain invariant under the dynamics. You can see it. Yes. So so f0 goes to f infinity. G equal to 0 goes to g infinity. So the set of these four lines remains the same. So in this case, we can talk about it as an inaccessible divisor. So it's closed under dynamics. So in fact it is accessible, but we can remove it just just without any problems. So and when we go during our dynamics, yes. So f tilde g tilde we will obtain just a similar picture, and so but we have that this two is a bit shifted and this two is a bit shifted. And we are asking maybe there could be so there cannot be new blow-ups. There cannot be a new blow-ups outside of exceptional divisors, because we can we can, using the formulas, calculate calculate the pre-image. Yes, but in fact, we can have some blow-ups on the exceptional divisors here, and here we should blow it up. uh, uh, so let me say it in another way. So so this is a dynamic. This is a new shifted blow it up space, and for this space we can have some u 0 over 0, which cannot be seen in the pre-image, which cannot be seen here, and so we should blow up more than an 8 points. But this is not the case. Why? Because you can see that the pre-image of new exceptional divisors is not exceptional divisors. It is just ordinary. It is just ordinary curves here. Yes, which was when G, which was even without blow-ups. So, for example, so for example, the pre-image of any exceptional divisors is 2-1 curve or 1-2. I think it depends on the line where the exceptional divisor is 2-1 curve, which passes through 5 blow-ups. Yes. So its self-intersection is -1, as it should be. So in this case,
What do you mean by 2-1 curve?
2-1 curve is this, that it is power 2 in F and power 1 in G. This is B degree.
Okay.
Yes. So of exceptional divisors in the F to the, so we have translation, and for translated equation and translated point we should blow up. Yes.
G bar or F bar equals to some particular numbers, so that we go to the block one. In this case, it is F equals to 1. Yes. This particular point.
Why F equals to 1? No, I'm yes. So for example, I say let us take point where
for this specific point, like G bar equals to a straight inverse.
We should in fact write equation in blowout up coordinates, and then so because there is not enough time, you should believe me that it will be to one curve which passes through the blow up points. So so it means that
No, it's actually clear. You need to have you want to find the sandwich of some point on this exceptional device. So you say a new G, G over line equals to some specific number, like A is straight inverse. Yes, and you need to find an equation of F and G.
Mhm.
That will this line. And to take the second equation, and it tells that G times specific value of G over line times the denominator on the right hand side equals to the numerator on the right hand side.
Mhm.
So
Yes.
2, 1.
Yes.
Where the degree,
That's
2
right.
is the degree of G and 1 the degree of F.
So
Or vice versa.
so so we have that from this we can see that that we haven't any new blowups. So so maybe it's not clear why I'm talking about it, but for example for the for the Painlevé 1, if you write the equation just in this manner, you will see only 4 blow-up points, and the four other will come at the next step. So what we have. So we have surface type A31, and you can calculate that the orthogonal one will be D51 symmetry. Here is it. So so the symmetry group of this equation will be W equal will be W affine extended D5. So it's generated by all this S and also by aptomorphism P, which is of order 4. This aptomorphism is acting in the following manner. It's of order 4. So so in fact we can extend this group even more because there are also another automorphisms of Dynkin diagram. For example, we can change only these a's. Yes. So if you take p square, you will change this and this together. But so if you want automorphism to change only one side, then you will obtain that root variables and q is inverted. So if we want to preserve q, the symmetry group is as follows. So, and inside, so now we can go, we can look at the picture from the another direction. We can say that we have such space which have some symmetries, and this space, so this is a fine symmetry. This means that we have translations, and if we calculate this translation, then we will obtain the following equation on coordinates and root variables, and it will be just some dynamics on letters to make it equation. We should add a relation of the form that W of f of A is f of W of A. So maybe T, just translation. Translation.
Translation.
We take this translation. We can, of course, take another translations, but there are finite number of shortest conjugated translations here. In fact, I forgot, is this a unique translation, or there are two? For E8 there are one, there are unique, but here I'm not sure. If it's unique, yes. If it's not unique, no. So it's it's not very hard to check. Is it true? So a bar. Sorry, a is a vector, not a bar.
So these are the roots.
Yes, root variables. They are the root variables are conjugated to the roots in some sense, so they have definition as some integrals. So we take our form, canonical form, take its residue on the component of exceptional divisor, and calculate, using this residue, calculate, for example, the slice, and call it A3 to minus 1, something like this. This is called period map. Okay, so Mm. So,
More or less a quarter of hour.
hmm?
You have more or less a quarter of hour.
Ah, okay,
15 minutes.
okay. So, mm, so nevertheless, I forgot. Have I, in previous talks, present you the calculation of background transformations or not? Calculation of background transformations from the geometry. It's bad because it's very important. So nevertheless, maybe I have presented, but if you don't remember, this is the same that I have. Okay, so in terms of Picard lattice, this is HF minus E37, HG minus E15, E5 minus A6, A1 minus A2, E1 minus E2, E7 minus E8, and E3 minus E4. So, so these translations are in fact very simple because they just they just change. For this translations are very simple because they just change, for example, E5 to E6 and, and so on. But what I want to, let me find. Okay, so 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 the, in terms of geometry, this is very simple. Yes, so for example, if we take so I should write, for example, this is E1, this is E2. Yes, so if we change, if we take S5, yes, we see that we should make such transformation which act trivially on HF and HG, such that these two exceptional divisors will interchange. How we can do it? So if HF and HG are still HF and HG, then the possible change of variables is only Möbius transformation. Yes. So, for example, we have f equal to some constant c0, and after this we have f s5f equal to some c0 tilde. So we believe that our transformation is birational. So to obtain from this curve So we have some translation. F goes to, sorry. So then we want to, so this is some expression with numerator, rational expression with numerator and denominator. So if we make it like polynomial, we know that it should be still 1-0 curve. Yes. So the numerator and denominator should not be of power higher than 1. Yes? Understand? So we have this curve. Then we make the transformation. We obtain some such curve. Then we want to write it in a canonical way. Yes? So we have that numerator equals C0 denominator. And we know that HF goes to HF. Yes, so it should be 1-0 curve. So the power of numerator and denominator is not higher than 1. So we have only Möbius transformation. But this Möbius transformation should preserve f equal to j equal to 0 and j equal to infinity, and f equal to 0 and f equal to infinity. Yes. So and this is only multiplication on some constant. So the S5 corresponds to some multiplication by constant. What constant? So when we make S5, these variables remain unchanged. So f goes to f. And here we have that 1 goes to a4. Sorry, maybe some mistake. Let's see. Sorry. Yes, of course. So it's S4. So now we are talking about S4. Yes. So we see that G should go to A4G. Minus one. Yes, minus 1. So so we see that. So what happens? We had point 1 A4, and we should obtain points 1 A4 minus 1, because F4 is a root variable which changes to A4 minus 1. So, and this is done by this transformation. And here we see what we see. We see that this is also divided by A3, A4 minus 1. Yes? So G is right. So, so here we have very simple transformation. So what happens if we take, for example, HF minus E37? Yes, we see that HF goes to HF, but HG goes to HF plus HG minus E37. So this is 1-1 curve which passes through points 3 and 7. What is points 3 and 7? So it is important this, and this. So, so let's see. Alpha fg plus beta f plus gamma g plus delta. We have 4 projective parameters, 3 ordinary parameters. So when g is equal to 0, we have that beta a2 is equal to delta plus delta equal to 0. This first relation. And the second relation is that it passes through the point 1 at g equal to infinity. So this means that alpha plus gamma equal to 0. Yes? Okay. So we see that because I put f equal to 1. Yes. So we have fg plus beta f minus g. Beta a2 equal to 0. So this is one parametric curve. In fact, it is projective, but I take only one. So we see that we have fg minus 1. Sorry. G f minus 1 divided by f minus a2, yes, with sign minus. Maybe yes. So it's beta. So it's like a new coordinate, but as I explained before, it is defined up to Möbius transformation. Yes. So let's see. Okay. Okay. So the correct answer is really such that here we have sign plus after Möbius transformation, and f goes to a2 minus 1. So from geometry you can obtain all the formulas. Okay, so finally the Sakai classification is that Sakai decided to classify to change the picture and classify all the spaces p1 times p1 blown up in 8 points, and this classification. So this is a constant. So we have the highest equation. It is elliptic. So its exceptional divisor is some elliptic curve. Then there is A01 star. It's elliptic curve nodal. And then have surfaces. So I will not let me draw this one, and so on. A4, A5, up to A8. So here we have 2A7, A7 and A7 prime. They are all fine. So, and this is Q Painlevé equations. And from here you have also D row, D4, sorry, d5, d6, d7, d8.
Sorry, so these are the configurations of the exceptional divisors
Yes.
on P1 plus P1 that
Yes.
need to go up in order to have good initial conditions.
Yes. So and in this part of classification is standard quality sense of Painlevé equations.
The lower part we already discussed.
So yes. So and finally, in 1 minute, I will explain you what is the limit. What is the limit of Q Painlevé to Painlevé from the geometric point of view? So this is the picture for Painlevé 6. If you compare it with this picture, and this is doubled. So this is just coefficient 2 because it's like d4. Yes. So what we can just do, we can take this one and rescale g such that g equal to 0 will go to g equal to infinity, and f remains f. That's all. In fact, that's all. That's the limit. So and if you take for example this dynamics T omega 2 minus omega 3, you will obtain the limit also difference dynamic, like d difference dynamic. But if you take conjugated, I forgot what, but some conjugated, you will obtain the limit the differential dynamics. Yes, of course. So we take f equal to f small and g equal to 1 minus epsilon g plus a alpha 2, where small letters and Greek letters is corresponding to differential Painlevé equation. I'm thinking, 1 moment. So
it's some block point.
yes, it is some blow up point. So you will see that this just say you that this point g equal to 1 is resulting to g small equal to minus alpha 2, and the other point a4, so the a variables is like e epsilon alpha something, so they are also small to 1, as close to 1. And just these blow-ups come together and become this double blow-ups.
Epsilon goes to 0.
Yes, because it's epsilon. Yes. So in other cases, the limits could be more complicated, but this is maybe the most natural limit. Okay, so I tried to make some brief review of how.
But so small f and small g are the Hamiltonian variables for.
Not Hamiltonian. Let me. There is like so f and j, maybe it's like ppq or something like that. So this is a result of some blow up and blow down. One blow up and one blow down. So that's because for PQ, for example, for PQ for Painlevé 6, you cannot draw for P1 times P1 normally. You should take some another surface. There are several peculiarities in this Sakai classification. That's why.
But is that complete or?
What I have drawn?
I think the original Sakai classification is the zone, no? But now is it known the rule?
Yes, so initial Sakai classification missed, I think, these equations. This is difference equations. I forgot A0, 1 to star, and it's A1 star. I forgot, so I never worked with this D difference equations.
Now it is claimed that after the classification is complete.
I think yes. I believe so.
Are there those difference equations which are not symmetrical of differential Painlevé equations?
Yes, they're not symmetries. There are some D difference equations.
From practice, I have say different over six and because of Painlevé six is just a different over five.
No. So for this equation D4, for this surface D4, we have from the one case it is space of initial data for Painlevé 6. From the other case, its translations is D Painlevé D4. D Painlevé D4. So in fact, if you take, it is like yes, you're right. So it's like D Painlevé 5, I think. But it's not. In fact, it's not a good idea to use such notations like D Painlevé 5 or Q Painlevé 6, because there are really many arrows. So in Sakai classification, you can almost make any arrow.
Why is it drawn with some limited number of arrows?
This is some very simple arrows. This is just some very simple arrows. Maybe you can, if you take some limitations on what is understood under the arrows, you can draw it in some standard way, but I'm not sure that even in modern sources it is written. The arrows is drawn with some idea.
Actually, I don't understand. So usually when the people draw some arrow, they mean that there is some one parameter degeneration. To take some parameter and send it some specific value.
Yes, yes.
So, for example, if you take just as the generation diagram for a differential convolutions, or even the generation diagram for a checker with geometric functions, we can not control any arrow except those which are already drawn.
So, so yes, there is the original arrows. I think really is drawn between the equations which differ on one parameter which we are scaling to infinity or zero. But I just want to stress that, for example, if you take Q Painlevé 4 with some special conditions, its limit will go not to Painlevé 6 but to Painlevé 3D, for example, so on. There are so the number, the generations is very. I don't know. Can it be formulated as a scientific question? But maybe yes. So, to classify all the generations.
Well, actually, I started to think if you want to do several generations in one turn, can we do something like this? Take parameter of the first generation to be epsilon, parameter of the second generation to be epsilon squared, or maybe vice versa, and then write some formulas with this complicated transformation.
So you're just asking about can we take two arrows and write one formula for it? Of course, yes. That's one of points that I'm stressing here. For example, yes, yes.
Okay, so maybe we can take Anton to see the vectors.
Thank you for
And see you next
listening me. Okay, so